All right, well, welcome back. We are on the final stretch now. We'll be starting Unit 6 today, which is going to be primarily Chapters 7 and 6 in your book. This will be on applications of integration. So we're going to be doing 7.1 today, which is going to be the area of a region between two curves. All right, so instead of just looking at the area of a region between a curve and the x-axis, now we're going to try to find the area between two curves. But to start us off, let's do a review example here. Let's say I have just one function, f of x equals 2 minus x squared. Recall this would be a parabola that's concave down since your leading coefficient is -1. And let's say I want to find the area under the curve. And remember, by area under the curve, I mean the area made between the curve and the x-axis. All right. In this case, let's take a look at the area above the x-axis here. So the first thing I want to do is find where the curve intersects with the x-axis, right? So essentially where the curve intersects with the line y equals 0. So let's take 2 minus x squared and set that equal to 0. Should have two solutions, right? If I add x squared to both sides, I get 2 equals x squared. Square root, take the square root of both sides, but remember, anytime you introduce a square root, you need plus or minus. So my two x-intercepts are going to be plus or minus the square root of 2. All right, so if I want to find the area under the curve, what I essentially want to do is take an infinite number of really thin rectangles, right, and add up all their areas to get the area under the curve. And we can keep going here. So I want to take this idea and go all the way across. So if I want to take an infinite sum, that's represented by an integral, right, that elongated s. And in this case, I want to sum up from x equals negative square root of 2 to x equals positive square root of 2. And I want to sum up a whole bunch of rectangles, right? Each rectangle has a varying height. The height is dependent on whatever the y value is here on the function, right? So in each case, the height varies, but it's always equal to f of x. In this case, 2 minus x squared. So it's dependent on where I am on the x-axis. Now the width is always what? It's a teeny tiny, infinitesimally thin dx, right? So this is how I would find the area under the curve, where f of x equals 2 minus x squared, and we can do that either by hand or using a graphing calculator. Today I'm going to be more interested in the setup than the actual computations, so I'm going to leave most of the computations up to you. So again, what does each piece represent? Integral is an infinite sum from x equals negative square root of 2 to x equals positive square root of 2. I want to sum up an infinite number of rectangles. Each one has height f of x and teeny tiny width dx. Okay. All right, so let's try one of the new examples here. What if, let's say I still have that f of x equals 2 minus x squared, but this time, instead of wanting to find the area between f of x and the x-axis, I actually want to find the area between f and g, where g is equal to the identity function x. So I would like to find this area here, right? I'm still going to sum up an infinite number of rectangles, right? In this case, you can see from the graph that I want to go from here to here. So it looks like x equals -2 to x equals +1. To find that algebraically, how could I find those 2 points algebraically if I wasn't given a graph? we could set f of x equal to g of x, right? Okay. Why don't we go ahead and do that? So let's get 0 on one side. So what multiplies to be -2 adds to be +1. We would have x plus 2, x minus 1, right? So my the x-coordinates of the intersection points would be -2 and 1, just like it looked like on the graph there. Okay, so I still would like to take an infinite sum. This time I'd like to go from x equals -2 to x equals +1. And I do want to sum up a bunch of rectangles, right? But this time, each rectangle goes, the height goes from the red to the blue, right? Whatever the y value is here, minus whatever the y value is here, right? Take a look at maybe this rectangle as an example. This rectangle clearly has a height of 2, right? This y value minus this y value. Okay. Similarly, this rectangle here, this cross section, has a height of whatever the y value is for f of x minus whatever the y value is for g of x. All right. So in each case, I want to take the top curve minus the bottom curve to get the height of the rectangle. So in this example, it'd be f of x minus g of x, right? That would be the height. And the width is still going to be an infinitesimally thin dx. Okay? All right. Why don't, so if I want to find the actual answer, right, I can just plug in f and g, so 2 minus x squared minus x dx. And then to find the answer here, we could take an antiderivative, plug in 1 and -2 and subtract, right? Or you could find this on your calculator. Okay, most of the problems in your book are going to be by hand. So I want you to find these by hand. However, on the AP exam, oftentimes, especially on the free response question, it'll be setup only. And you're done at this point, okay? If the functions were given as f and g, you can leave it like this, because that was part of the stem of the question, all right? When you're finding area between two curves, you are never going to get a negative answer. And here's why. Think about, even though, let's say you have a height of like approximately 1/2 here and approximately -1 here. If you do top minus bottom, so if you do 1/2 minus a -1, you're going to get a +1.5, right? So unlike area under the curve, just area between the curve and the x-axis, where you can get negative area, in this case, you're not going to. Okay, so if you do get a negative area, something went wrong if you have two curves. Okay, let's set this one up. It says, set up the definite integral that gives the area of the region bounded by the given functions, find the area, give your answer as a decimal accurate to 3 decimal places. So in this case, just set it up and then you can find the answer in your calculator, and I'll let you do that on your own. So let's set it up. The difference here is we don't have a graph this time, right? So we're going to need to figure out what the top function is and what the bottom function is. And we can actually do that without a graph. We can do that algebraically. But the first thing I'd like to do is see where the two graphs intersect, right? So to find the points of intersection, or the x-coordinates of intersection, let's set f of x equal to g of x. Right? Okay. So if I subtract 2x from both sides, then I actually get x squared plus 1 equals 5. And then I can subtract 1 from both sides, and I get x squared equals 4. Take the square root of both sides. Don't forget your plus or minus. So my 2 points of intersection are plus or minus 2. Okay. So I know my integral is going to be the integral from -2 to +2. And I know I need top minus bottom, right? I'm just going to do t minus b dx. So now I just have to figure out, is f of x the top or is g of x the top? So any ideas on how I could do that without having to produce a graph each time? Well, I know that they only intersect, these graphs only intersect at 2 points. So why don't we take a point between -2 and 2 and find the y values there, and that should tell us which one is top and which one's bottom, right? So pick a nice value to work with between -2 and 2. Easiest one is probably 0, right? So if I find f of 0, what do we get there? Just 1, right? If we find g of 0, we get 5. So since 5 is greater than 1, g is the top function and f is the bottom function. So my final integral is the integral from -2 to +2 of g of x minus f of x dx. And I'm going to leave it like that. Since f and g were defined in the problem, it's fine to leave it like this. Okay. If we want to find, if you're using a calculator to find this, I really recommend putting like f into y1, g into y2, and then using your variable button to grab y1 and y2 into your home screen when you're typing this in. And that is because I just see too many problems with parentheses. If you don't do it that way, it's a little bit too much to see on the screen. So really use your Y1 and Y2 buttons. Okay. This example says sometimes the curve intersect at more than 2 points. So in this case, I'd like for us to find the area. Again, we're just going to do setup only. Okay. So first things first, let's go ahead and find where these graphs intersect. So let's set f of x equal to g of x. Okay, if I add x squared to both sides, I'm left with 3x cubed minus 10x on the left side equals 2x. Okay. Ideas? Let's get 0 on one side. So let's subtract 2x from both sides. That'll give me minus 12x on the left. Okay, now what? Why don't we go ahead and factor out the common factor of 3x? So that leaves me with x squared minus 4 times 3x on the left side. And why don't we go ahead and continue to factor here? That factors into x plus 2, x minus 2, right? So in this case, I do have 3 intersection points because I can set this factor equal to 0 and get a true statement of x equals 0, right? So x equals 0 is one of them, -2 and +2. So I'm going to write them in increasing order there. Okay, so what does this mean for our integral? Well, think about this. If you have 2 functions, and let's see this one. So let's say I have some function here, and then another function that goes like this. Okay, did you see how top and bottom switched there? So if you have more than one intersection, your top and bottom could change, right? So I'm going to need to set up 2 integrals and then check to see which is the top and which is the bottom for each piece, okay? Now they don't have to switch, right? This one could have just stayed on the bottom like that, but they very well could. And I don't have a graph, I don't have a picture of what's going on, so let's look at this algebraically. So I know I'm gonna have 2 integrals. I'm gonna wanna add like this piece and this piece. So the first one's gonna go from -2 to 0, top minus bottom dx, right? And then I want to add the second piece, the second area, and that one's going to go from 0 to +2 of top minus bottom dx. Okay, so let's figure out the top and bottom in each piece. Okay, so for the first piece, I'm going from x equals -2 to x equals 0. So pick a number between those. Shall we do -1? So f of -1 is going to be -3 minus 1 plus 10, right? So that's going to be 6. And then g of -1 will be -1 minus 2, which is certainly less than 6, right? So for the first integral, the top function is f and the bottom function is g. So for the first integral, I'm going to go from -2 to 0 of f of x minus g of x dx. Right? Okay, now let's test a point on the second integral. So the second integral goes from 0 to 2. So let's test x equals 1. So f of 1 is going to be 3 minus 1 minus 10. Right, so 3 minus 11, looks like we get -8 here. And then g of 1 is going to be -1 plus 2, which is greater than 8, right? -8, sorry. Okay, so for our second one, top and bottom did switch, right? So for our second integral, I want to take the sum from 0 to 2 of g of x minus f of x dx. And that's my answer there. Okay. All right, so I have kind of the directions of what we did on the bottom here. So first, find the intersection points. And how do we do that? We set f and g equal to each other. and determine which function is top and which is bottom. And you will have to do that for each integral you have. So if you have more than one integral, you're going to have to do that more than once. All right, and then set up an integral expression for each area and add the areas together. Okay. All right, sometimes the functions are in terms of y instead of in terms of x. Okay. So let's take a look at this, this problem here. It says f of y equals y plus 1, and g of y equals 3 minus y squared. Okay, so now instead of taking top minus bottom, I want to take my cross sections like this. I'm going to sum them up like so. So what would I do in this case? In this case, I would want an infinite sum from A to B, whatever my intersection points are, of right minus left. And in this case, I want to sum up, so my width is right minus left, and my height is a teeny tiny dy, right? Okay. However, the process is going to be exactly the same, okay? Even though the rectangles are horizontal instead of vertical, we're still going to set the functions equal to each other to find the intersection points. We're going to take a point in between the intersection points to figure out which one's farther right. Whichever one's larger will be farther right. And then we're going to set up our integral accordingly. Okay. All right. So first thing I want to do is see where these functions intersect, or where these relations intersect. So I have y plus 1 is equal to 3 minus y squared. Okay. Looks like I have a quadratic with both a y squared and a y term. So I'm going to get everything on one side. Okay. Looks like we have the same factorization as before, right? Y plus 2 times y minus 1 equals 0. So y equals -2 and +1. So just 2 points of intersection. So I just need to take 1 point in between and find which one is larger. So my integral, I know, is going to go from now y equals -2 to +1. Remember, all your variables here must match. Okay. So 1 point in between would be 0, right? That'd be an easy one to check. So f of 0 is going to be 1, and g of 0 is going to be 3. So g is to the right, which is verified by our graph here, right? So g of y minus f of y dy will be our final integral. Okay. What would have happened had I tried to take vertical cross sections in this case? You see what would happen right about here? It would have worked until this point, right? I would do green minus black, top minus bottom. But then here I have black minus black, right? So it is doable, but it would take quite a bit more work. And so this one really leads itself well to right minus left. You just have to remember, if you're going to do right minus left, everything must be in terms of y's. Okay, and I believe that is all I have for you. Just be sure that, and I have this in your calendars too, but for 37 through 47, please show all integrals. Okay, and that's it for today. So hopefully that was a pretty straightforward lesson, and I will see you all next time. Good luck.